Now, when we inspect the model summary for a GLM, right? Now that we understand what the coefficients are doing, and we know that they are on the link scale, not the response scale, so we need to transform those if we want to make any sense of them. But apart from the coefficients, right, being a little bit different, there's another thing about this summary output that's a little different. If you scroll all the way down to the bottom, you'll notice that there is no r-squared value and no p-value, right? The summary output for a linear model, an LM function object, will include an r-squared value and a p-value, but this summary output for a GLM does not. Right? The reason for that, as we discussed in the lecture, is that GLMs are fitted using a different approach, right? Because they're making use of maximum likelihood estimation, which you don't need to know much about, but it's a different way of fitting the model. You can't calculate r-squared values and p-values the same way that you can for an LM. And so the model summary output here doesn't report those values because they can't really be calculated in the same way. But we still can find a way to get a p-value and an r-squared equivalent for this model. What we want to do, though, is run what's called a likelihood ratio test. Now, a likelihood ratio test is basically a statistical hypothesis test that compares our model to a different form of the model, of our same model. So if we want to get a p-value, this is how we would do it. We take our model and we actually strip it down, right? So instead of having our GLM of the left tibial plateau breadth as a function of crural from the Goldman data and family equals Gaussian link equals log, right? This is our GLM that we had above. So this is what our model is, and we want to get a p-value for it. So what we do is compare it to this model, right? I just replaced crural with the number 1. What that is an intercept-only model. As a function of 1, right, tilde 1 means intercept only. It means that we're predicting LTPB based on only the intercept, not on any coefficient for any other predictor variable. There really is no predictor variable here. So this is an intercept-only GLM. If we plot this, we can see, let's grab, let's make a plot here. So we've got the plot of the LTPB as a function of crural data equals Goldman. Let's extend the y-axis here. So we've got our data. I've just extended the y-axis a bit so we can see things a little bit differently. Now let's plot that intercept-only model. Look, it's all the way down there near 0, and it's just a perfectly horizontal line. That's because this is the intercept, right? That LTPB value being plotted here is the intercept from our model, but there is no slope, so there's no effect of the crural index here. This intercept-only model is basically the null hypothesis for a likelihood ratio test, at least in our case. What we're then doing, let me go up and grab our model fit from above, is we're comparing this intercept-only model to our actual model, right? So the intercept-only is in red, our actual model is in blue, and we're treating the red model here as a null hypothesis and comparing our model in blue to it. And we're trying to see if including a coefficient for crural index actually improves the model in any significant way. And this is how we're going to get a p-value. And so in order to get this p-value, we need to install another package. We need the LM test package. Now there's a couple different functions out there for likelihood ratio tests, but I kind of like this, the one that's included in this LM test package. And specifically, the function is called LR test, likelihood ratio test. So if we load that LM test package and then we inspect the LR test function, you'll see that it just takes, at minimum, your model. You can specify other things and other models if you want to compare two different nested models to each other, but we're just comparing it to an intercept-only model, and so we can get away with just doing this. You'll see then that this spits out an output where it lists our model 1, LTPB, as a function of crural. That's our actual model. And then the function itself creates that intercept-only model for us. So whereas before I made one called int.only, this function actually does that on its own. It strips down our model, gets rid of crural, and replaces it with a number 1 to make it an intercept-only model. We then have a breakdown here, and the important part that we're looking for is this p-value here, right? The probability of our data, or more extreme, on a chi-square distribution. This p-value, 0.037, right, is obviously significant at the 0.05 level. So we actually have a significant model. It might not look like much is going on here, but the model is significant. To report this, right, we would want to give the chi-squares test statistic, which is 4.35 right here, and we would give the degrees of freedom, which is 1. It's showing up as -1 here because it's taking the degrees of freedom of our full model and the degrees of freedom of the intercept-only model, and seeing what the difference is in degrees of freedom between them. And because we're stripping away the crural coefficient to just an intercept, we're down 1 degree of freedom. And that's why it says -1, because we've lost a degree of freedom. But you can report this as 1 degree of freedom. So it would be chi-square equals 4.35, degrees of freedom equals 1. P is less than 0.05. That would be how you would report the results of this likelihood ratio test. And I often put LRT : and then I give those statistics so that somebody reading this knows that they're reading the results of a likelihood ratio test. And so, yeah, this is how you get a p-value, right? This p-value is telling us that our model, our full model, that includes crural as a predictor variable, is performing significantly better than an intercept-only model, right? It's a significant improvement over just that null model that we've got here. And so this is how we get a p-value for a GLM, at least one of the ways. As I said, though, you'll also notice that there's no r-squared value in that GLM output, but we can get a different form of r-squared value for this model. Now, there are what are called pseudo r-squared values out there, a whole bunch of different ones, McFadden's, I think there's like Cox-Nagelkirky, there's a bunch of weird ones. There's a lot of debate as to just how applicable those are. But one of the better options for kind of an alternative to r-squared, because again, we can't calculate a real r-squared for a GLM, because it's being fitted in a different way than a linear model is, because we're not assuming normality anymore. I want to calculate what's called the deviance squared, or d-squared statistic. In kind of GLMs, whereas an r-squared value, I should say this first, in LMs, right, an r-squared value is an expression of the proportion of the variance in LTPB, in our response variable, the proportion of variance in that is explained by including our predictor variable in the model. So including crural index in the model will explain some percentage of LTPB, and that's our r-squared value, right? But in a GLM context, right, that definition doesn't quite make as much sense as it does in an LM context, because we're doing things differently. It's a different way of creating and building a model. And so this d-squared statistic is actually deviance squared, and it's dealing with this concept of deviance, which again is beyond the scope of this module. But you can think of it as kind of the unexplained fit, right? It's sort of the lack of fit, in a sense, of our GLM. Whereas you could make a model that fits our data perfectly by including a separate parameter, a separate slope for every data point in the model. That would be a perfect model, but it would be so overfitted that it's not really useful in any way. We're just describing the data with a really complex model. That would be silly. But that would be a perfect model. That model would have no deviance because it's perfect. Our intercept-only model, then, in contrast, has no other parameters other than the intercept. So it's got kind of all the deviance, so to speak. That difference in deviance, then, of what's left unexplained between a perfect model and our intercept-only model, that deviance is what we're trying to explain away by including Krull index, for example. And so by including the Krull index, we're explaining a portion of that unexplained deviance. And the proportion of that unexplained deviance that the Krull index can explain, that's the d-squared statistic. In order to get this, we need to load another package called the mod ev package. I think it's called model evaluation and analysis or something like that. So if we load this package, we want a function within it called d-squared. And just as with the likelihood ratio test that we ran, we feed it our model object to this d-squared function. Again, you can inspect the d-squared function on your own, pull up the help page for that. But this is going to give us this deviance squared statistic, this d-squared statistic, which again is the proportion of the deviance, that kind of unexplained stuff, that the Krull index is capable of explaining when we include it in our model. So if we run this, we get a value of 0.003. That is bad, right? That's very low. That means that our Krull index here is explaining not even 1%, not even 0.5%, but 0.3% of the deviance that's left over in LTPB. So our model really isn't good at explaining hardly anything about what's going on with the tibial plateau breadth. Krull index does not do a good job of explaining that. But you might say, right, if it's not doing a good job, how did we get a significant p-value, right? We got a p-value of 0.037, but then our d-squared value is terrible. How is that possible? And this is why it's really important to keep the definitions of these two statistics in mind, right? A p-value, as we've said many times, and I'm going to say again, is the probability of your data, the probability of your result, assuming the null hypothesis is true. And so that p-value of 0.037 in this case just means that our result is very unlikely if that null hypothesis were true. That null hypothesis, of course, here, this intercept-only model, is obviously not explaining anything about our data because it's all the way down here, this red line. And so, of course, it's not doing a very good job. But what the d-squared statistic is doing is not saying anything about how likely or how unlikely something is to occur. It's saying how much of the deviance is actually explained by including this. There are two terms here that are kind of important. The p-value is giving us statistical significance, as we've said. This is whether our result is likely or not if the null hypothesis is true. But a d-squared value, similar to an r-squared value, is telling us something more about practical significance, not statistical significance in terms of that formal definition, but practical significance in terms of, is this effect actually meaningful in a real way, right? Just because something is unlikely, just because our model is unlikely, our result is unlikely, our data are unlikely, that doesn't mean that they're actually meaningful or practically significant. So this is a case here where we've got a p-value from our likelihood ratio test that is significant, but our d-squared value is very, very, very low. This is a case where we have statistical significance, but no practical significance, right? There's really nothing going on here in any meaningful sense, right? Just because our model's unlikely, that this result is unlikely, doesn't mean that it's really meaningful in any sense. And so this is why it's always important to not just look at p-values per se, but to also look at these other test statistics like d-squared or r-squared to see if you've actually got something meaningful going on here, or whether you've just found an unlikely result.